Okay, well, thank you. So I would like to remind you of a few things. So what we considered was the FBI transform. So I will just write now and I will not worry about the prefactors now for this talk. 2h z minus x u of x dx. And just like in Alex's talk, if u is a distribution, this is of course meant as a distributional pairing. And then we defined the analytic wavefront set. So u is a function in S prime of Rn. So that implies that this THU of Z is bounded just by looking at the semi-norms of this Schwartz function in X is bounded by some negative power of H, Z to some positive power, E to the weight, which is 1/2 imaginary part of Z squared over H. And then we define the analytic wavefront set of a distribution by saying that x naught, psi naught, is not in the analytic wavefront set of u if and only if there exists some u neighborhood in Cn of x naught minus I psi naught and delta positive such that we gain compared to this overall weights. And of course, oops, sorry. And this is as uniformly as H goes to 0. Huh? So U is here, I will not in my talk in the afternoon, but in the talk so far, U was always independent of H. Huh? So what we had was this. And we proved that, in the beginning, we proved that the analytic singular support of U, so this is the complement of the set of points which have a neighborhood in which U is analytic, is the projection of this wavefront set. And that was one thing, and then we almost proved under some assumptions is that the wavefront set, if we have some operator P, A alpha of x, Ex alpha, A alpha are analytic. So this could be a local statement, so in some omega. Then what we have is, what we have is that the wavefront set, so U is a distribution in omega. So this can always be, localized. This is a local statement. So then what we had was that the wavefront set, analytic wavefront set of U, is contained in the analytic wavefront set of PU union the characteristic set of P, where this set here is defined as the set of X and Xi different from 0. I should also stress here that Xi naught, I will say somewhere Xi naught equal to 0, but the wavefront set is a subset of the, as in other talks, of the 0 section removed, where this is the leading part of the operator A alpha X psi alpha is equal to 0. And today, I would like to prove, Kashiwara's theorem. Please. Which one? This one? Yes. Yes. Well, yes, because it is also true. I think it's in Hermande's book. Huh? In any class, that he has these generalized classes. I believe so, yes. So Kashiwara's theorem says the following thing. So this is the watermelon theorem. Says that suppose So this is local, but I'll state it for Schwartz function. And support of u is contained in x1 greater or equal than 0. Huh? So support of my function is in 1/2 space. Then say 0, but any point, you know, on the boundary here, 0 psi is in the analytic waveform set of u. So psi in Rn minus 0. That implies that 0 psi plus TE1 is in the analytic waveform set of u. Well, strictly speaking, I have to exclude the case when this is equal to 0, but you know, okay. So for all multiples of t, for all t in R. Okay. Now, why is this called a watermelon theorem? Here is a watermelon. Okay. This is the direction of psi. This is E1. Okay. E1 is here. Everybody's with me here. E1 is here. Now suppose, so this is now a unit sphere in psi. Unit sphere in psi. Suppose I know that I have an element psi in the wavefront set. I didn't remind you, but this set is radial in the sense that if x naught psi naught is in the wavefront set, then the whole ray through it is in the wavefront set. So wavefront set is this whole line here, so I might as well look at this. This is psi1. What this theorem says, that the whole slice is also, actually it's better to do not in the wavefront set because wavefront set is a closed condition. You see, I should have said that, say this, a statement is equivalent statement, so this is just logic, is that statement is that if 0 psi is not in the wavefront set, so this is again under the assumption that support of u is contained in x1 greater than or equal to 0, then 0 psi in the wavefront set of u implies, not in the wavefront set of u, implies that 0 psi plus TE1 not in the wavefront set of u for all t in R. It's an equivalent statement. So you see, so now, if this point is not in the wavefront set, what? Well, yes, but it's equivalent because you see, if I know it for every t, it's just apply some logic. In any case, so now you see, suppose this is not in the wavefront set, then I know that the whole slice, so this is E1, the whole slice is not in the wavefront set. And this is why it's called the watermelon theorem. And we are going to prove it. But let's first think about some consequences of this theorem. Suppose that instead of x1 greater or equal to 0, we know that support of u is contained in f greater or equal to 0. But f is some C2 function or C2 function. We can always replace this f, in fact, by an analytic function. In fact, we can replace it by a second order polynomial because, you know, you can replace f by f2 Taylor up to 2 plus just, you know, x, if I'm at some point x naught is f of x naught is equal to 0, I just put this, add this, and then it will be contained inside of, if it was f here, it will be contained inside of f, this new f greater or equal to 0. Okay? So in other words, we might as well assume f is analytic because, it's a polynomial locally. This whole thing is local. So what this implies that if f prime of x naught sorry. So before saying this, let me say something else. And one implication of this is that by letting t go to plus minus infinity, this implies then that 0 E1 plus minus E1 is in the wavefront set of AU. So same thing. So if there is some psi which is in the wavefront set of U, then it implies that this is also in the wavefront set, because what we do is we let t go to infinity, the set is radial and closed, so this goes away, and we just have plus minus E1. So what this means in this case is that this implies, so we basically then, assuming that f prime of x naught, the df of x naught is different from 0, we now have, we make a change of analytic change of variables, so this becomes x1, and then what we see is that E1 corresponds now to the differential of f, so this implies that, so what we have now is that wavefront, some point is in the wavefront set of AU, implies that x naught, psi naught, there exists psi, that x naught, df x naught plus minus is also in the wavefront set A of U. Huh? Okay? Just simply by using this corollary here. So this leads to the following definition, which is the following: n star of k. K is an arbitrary closed subset of Rn. Closed is the set of points x psi such that inside of inside of the boundary of k cross Rn minus 0, such that there exists f in C infinity or C2, such that f restricted to k has a local minimum at x, which is in the boundary of k. So this is basically the same thing as this being 0, and the local minimum would be 0 at the boundary. So what do those sets look like? Basically, what you do is you take a closed set, you look at the point on the boundary, and you want to fit it against any, you want to put any hypersurface, which the set lies only on one side of this hypersurface, and you look at the normals. So example, let's see, I hope I got it right. If k is this, what is the n star of k? Well, n star of k, and sorry, I should say, and I didn't say what psi is, sorry guys. Psi then is plus minus df of that point. Huh? So in this case, what we have is, of course, I can fit this, on one side of this straight line, on the one side of this straight line. So I have all the directions here. So what I get is the conormal to x equals 0 intersected with y non-negative, union conormal of y equals to 0 intersected with x negative. And then, of course, here I can put any line, if you like, and this will be on the side of any line like that. So in fact, and since I can take plus minus directions, I get the whole fiber over 0. Yes, because I can take, any direction here, and negative directions count as well. On the other hand, if I take this set, okay, then in this case, I only get this part. So this is not maybe not the easiest and certainly not the only way to use this observation based on this theorem to show the following theorem, which is due to Sato, Kawai, Kashiwara, is that if I have U a distribution, let's just keep Schwartz, it's a local thing, sorry, Rn, then n star of the support of U is contained inside of the wavefront set of U. And the reason for that is simply this, that any point at the boundary of the support cannot be in it has to be in the singular, analytic singular support. Because you got at the boundary of the support, you can't be analytic there. So there has to be some wavefront set above the fiber. That's this first thing over there. But if there is a wavefront set above the fiber, this means that I have some point psi, but then we have that the normal is in the wavefront set. Now you take any choice of this f, and you get your n star of k. And this is sort of a generalization of Holmgren, the theorem. If pu is say equals to 0, this implies that n star of support of u is contained in the characteristic set of P. Okay. And there are many refinements. So let me tell you one. So this is a theorem of Spectral from 40 years ago, which says that it seems a little strange at first, that suppose F is C infinity on the cotangent bundle. So it's local, but I will write like this. And F restricted to n star of k. K is an arbitrary closed set, is equal to 0. This implies that if you flow by the Hamilton vector field, you start with some point rho is in n star of k. You flow by the Hamilton vector fields of T. This is in K. This is in n star of K for some time. Okay. So this is a purely geometric statement. The tricky thing is that this is an arbitrary closed set. Huh? If, for instance, K is x1 greater or equal to 0, you check it immediately from the fact that you will vanish on if a function vanishes on a conormal bundle, which is a Lagrangian submanifold, HF is tangent to that submanifold. Huh? So that's the sort of generalization. Now, why this is interesting? Because then Bonny, before proved this. This is a generalization of the result of Bonny, who showed the following thing, that suppose f and g are smooth functions, and f restricted, and f and g restricted to this k is 0, well, this implies that the Poisson bracket of this guy is restricted to n star of k is also 0. Huh? Because Poisson bracket, so, maybe Poisson bracket is the Hamilton vector field applied to G. So that's the Poisson bracket. So in other words, since it stays tangent to this, you have something that vanishes on it. You differentiate with respect to T. It has to be 0, the Poisson bracket, because that's just HF applied to G. Now, why is this theorem interesting? Because this now implies unique continuation for operators that normally would not have unique continuation. So suppose you take P, famous operators in some circles. This is an operator which is not elliptic, but we look at the characteristic. We know now that if I have Pu equals 0, then this implies that analytic wavefront set of AU has to be contained in, so we know now that n star of the support of U has to be contained in the wavefront set of U, and this has to be contained in the characteristic set of P. Now, you see, all of these terms are non-negative. So the characteristic set of P, we know that Xi1, Xi2, and X1, Xi3 vanish on the characteristic set of P, yes? But we now know, so they vanish on this set. But then Chester and Bonny tell you that, told us 40 years ago or more, that Poisson brackets have to vanish. But the Poisson bracket of Xi1 and this guy here is Xi3. So this implies that, you know, Xi1, X1, Xi3, which is Xi3, has to vanish too. But now you have to have Xi1, Xi2, Xi3 vanish, but that's impossible because we excluded 0. So this means that it cannot vanish anywhere. So this means that you cannot have boundary of the support. This operator has a unique continuation property. And what's interesting about this operator, that this operator is famously hyperelliptic. Pu equals 0 implies U is smooth, but it does not imply U is analytic. So this is sort of, this is kind of classical applications of this, but I will mention, you know, the other applications. So, and as I said, one can prove it without using this watermelon term, but I like the proof using watermelon. Okay, so let's prove it. Oh. So the proof goes as follows. We assume that 0 Xi is not in the analytic wavefront set. First of all, U is Schwartz, so this is a local thing. So I use the fact that I have this growth condition, and what I have is that I'm going to write it like this for simplicity, that this is less than or equal to, and rather than bother with those prefactors, we work now in a compact set. So in any compact set, I can replace the h to the minus n by adding a little epsilon to my exponent. C epsilon e to the imaginary part of z squared divided by 2h plus epsilon over h for z in any precompact subset of Cn and every epsilon greater than 0. Just so that I don't have to write all these things, huh? You know, if I have h to the minus n, it's certainly less than this for every epsilon. No, plus. It's worse. It grows exponentially, so it kills h to the minus n is bounded by this for every epsilon. This is a triviality. Sorry?
You're not using this?
No, I'm not using it. That's a general fact. Huh? And the second thing, and this I'm going to use it now, that th, u of z, is less than or equal to e to the imaginary part of z square over 2h minus delta over h for z in some complex neighborhood of minus I psi. That's my assumption. And now we want to use the assumption about the support of U. Okay? So for that, we look at the definition, and we look at z minus x squared. So forget about 1/2. So what it is the real part of minus this. Huh? Real part of that is equal to minus real part of z minus x1 squared plus imaginary part of z squared. Okay? And now, if x1 is negative and real part of z is also negative, real part, z1, I'm sorry, I forgot. And here I have real part of z prime minus x prime squared. So remaining, I look at the first component. So let's see, where do I gain? If x1 is negative, then this is positive. So when something real part of, if x1, I'm supported in x1 positive, so this is what I'm integrating, yes? But when real part of z is negative, then this is also negative then, on the support. So sorry, I want to say x1 is non-negative, real part is negative, then this is less than or equal to minus real part of z1 squared plus imaginary part of z1 squared plus imaginary part of z prime squared. So this is the trickiest part of the proof. Is this right? No? If x1 is non-negative, then this is negative. So if this is negative, I can, this is going to be, this is bigger than this. So when I put a minus sign, I get this inequality. So what this means is that we have the following fact, that TH U of Z is less than or equal to C epsilon E to the minus real part of Z1 squared over 2H plus imaginary part of Z1 squared over 2H plus imaginary part of Z squared over 2, Z prime squared. So Z prime are the remaining variables plus epsilon, again for every epsilon, over H. So these are the three things. Yes, please. Sorry, because it has a minus. I'm sorry. Sorry. It has a minus. sorry. No. Without a minus, there is a minus. Yes, thank you. Okay. So now we will use complex analysis, and the key point here is that this function. So key point is that the function z1 goes to imaginary part of z1 squared minus real part of z1 squared is the same as minus real part of z1 squared, and that is harmonic. So what this means that when we will now look at, what's the strategy? The strategy is we'll freeze z prime, and then we will take the log of this. Log of this gives me a subharmonic function now of z1. And you see, I can always add a subharmonic function to get a subharmonic function. But if I have a harmonic function, I can subtract it, and I still keep a subharmonicity. And we will use the maximum principle to get something out of it. So we just follow this strategy by taking a log. And applying, another kind of, not as completely standard. Jesus Christ. Sorry about that. Well, in this weather, it would dry up before the afternoon session. So we are going to take a log. So for this, I think I better use my notes because see, I prepare my notes with my glasses and I can't read them then without my glasses. So I'm going to fix z prime in a neighborhood in Cn minus 1 of minus I psi prime. So prime denotes all variables other than the first one. And then maybe before, let me translate what we have here on the log side quickly. So what we have is twice h log of t h u of z. This is so crucial fact, log of a holomorphic function is a subharmonic function, and subharmonic functions satisfy the maximum principle. So, but this one has the following bounds. It's bounded by imaginary part of z squared plus epsilon. For any epsilon, I won't write it. We fix this epsilon z in any compact subset of Cn. And it has this improved bound, imaginary part of z1 squared minus real part of z1 squared plus imaginary part of z prime squared for omega intersect with real part of z1 less than or equal to 0. This is our improvement based on the support condition. Huh? So I take this, and this we freeze it. We freeze it because, the theorem tells us what happens when we add something in direction E1. So we freeze it. And then what we have is now we are going to define W of zeta, sorry about that, which is 2h log th u of zeta z prime minus imaginary part of z prime squared, z prime is frozen, plus I did it real part, I think I have a misprint here, we'll check, zeta squared, because I have minus, that's right, minus this epsilon. The epsilon is arbitrarily small, so that doesn't really matter. So I defined this function. And now I want to see what sort of estimates I have on this function. Okay, so this is in zeta, this is a subharmonic function. Because I took a subharmonic function, this is just a constant as far as zeta is concerned, and then I added a harmonic function. I'm allowed to do, keep subharmonicity. So what are the estimates for this? I have that W of zeta is less than or equal to real part of zeta square plus. This is just the fact that you see when the real part of zeta is negative, I subtracted this term, I subtracted this whole thing. So I have bound is 1 plus epsilon, but I subtracted epsilon. And then when I'm above, well, I subtracted the imaginary part, but I kept the real part, so I get this. So this notation is sort of notation of Adamar, or Rees actually, this is the Rees notation, xa, x to the a, x positive, 0, negative. That's all this means. So this is true everywhere. And what I know also is that W zeta is less than or equal to the same thing, because plus, minus delta for zeta in the neighborhood of minus I psi 1. Okay? Because that's my assumption in the middle when I took the log. And maybe this is, I could put a different delta here. If I take a small neighborhood, this term does not matter because it's small and I have some negative gain. So this maybe is a different delta, but we can live with that, I hope. Well, actually, sorry, I use the same delta because this is a non-negative. So I have this. So now we want to apply some kind of version of the maximum principle. So it's sort of a propagation of negativity for subharmonic functions. So we will have the following lemma from complex analysis. Lemma. That suppose we have a subharmonic function. Well, I sort of remember now, but which is this. I will have I have some rectangle, well, not some, but a rectangle, zeta in C, such that the real part of zeta is less than B, and the imaginary part of zeta is between some y naught plus A and y naught minus A. And I have W, which is continuous, well, that's just pedantry, continuous in the closed, where it is closed, in the rectangle, and subharmonic. Subharmonic. And it satisfies the following estimate. That it satisfies the estimate W zeta is less than or equal to, and now we want to sort of use this type of estimate here, real part of zeta plus squared for all of the elements here. This is valid for in any compact set. Huh? And near y naught, we have an improvement, which we will choose it will be minus b squared over 2, where real part of zeta is less than b, and imaginary part of zeta is equal to y naught. I wanted to have a bigger picture. So what's the picture? And the conclusion of the lemma, okay. So this implies that there exists some gamma naught. I mean, there's a more precise way, but who cares? Gamma naught, gamma 1, which depends only on A and B, such that W, if you like, I write it now in this column, xi, y, is less than minus gamma naught, positive constants, I should say, gamma minus gamma naught, for, say, y naught minus, let's say, 2/3 or some such number, any number less than 1, really, plus 2/3 A, and x less than gamma 1. Let me draw a picture. The picture is we start with a rectangle like this. Here it's minus b, this is b, well, let me take, you mind y not equal to 0? Since I draw it like this, y naught is equal to 0. This is all translation invariant. Huh? This is then minus a, this is a, and what I know is that here my function here is negative with some controlled way. Here, W is less than minus b squared over 2. Okay? Here, here I know that my W is less than or equal to 0, because that's real part of Z plus is 0 there. Here, I know that W is less than or equal than real part of zeta squared. That's where. So the idea is to construct a suitable harmonic function that will add to W. And of course, you want to apply it in a region which is weighed towards where you have a better estimate, W. So you choose some gamma, it's supposed to be very small. Gamma is greater than 0, but very small. And then well, for technical reasons, you then take B minus gamma here. And what happens is that the negativity of this W propagates in the y direction. So there exists some region where W is actually, in the open region, it will be strictly negative. So then what we do, we take a little column here, and there it's strictly negative. Okay, and this column, goes up to say 2/3 or 1/2 O. And actually, it would go, if I make it narrower, it could go anywhere. So this is the picture. So I will show you in a moment how one proves this. But let's just see how it applies to our situation here. So you see, this is our W. It satisfies these assumptions. If I take B less than, I don't know what, I take B sufficiently small, yes, I take B, take A to be twice T. T will be our T in the theorem, twice T. Y naught to be minus psi, and B to be less than 1/2 square root of delta. Once that is so, then our assumptions here show that these assumptions are satisfied. Because I took B so small, you see, this is now B square minus delta, but B was smaller than 1/2 square root of delta, so this is less than or equal to minus 1/2 B squared, which is the assumption here. And this is the same. So what this implies that 2h log of t h of z u, which is equal to w zeta plus zeta is, if you like, z1 plus, I'm undoing what we did before, zeta press square plus imaginary part of z1 squared minus real part of z1 squared plus epsilon is less than or equal to. Now I basically make this into a minus gamma naught for real part of z1 less than gamma 1 and imaginary part of z plus I psi less than or equal to, whatever, 2/3 absolute value of t. Okay, because I just applied this theorem. Sorry, not 2/3, 3/2, whatever, 2/3 of 4/3. I mean, who cares? 4/3, any number bigger than 1 will do. It's 2 multiplied by 2/3 is 4/3. Okay, and then I have, of course, here, this is non-negative. This is an epsilon, which is arbitrarily small. So what I get here is imaginary part of z squared plus epsilon. But epsilon is arbitrarily small. So this means that this is less than or equal than minus delta prime plus imaginary part of z squared everywhere here. Everywhere here. So in particular, near, sorry, this is imaginary Z1, near imaginary part of Z1, Z1 equals to minus I xi minus I xi1 minus IT, and of course, Z prime was fixed. But this is exactly the statement of the theorem, because that means that the FBI chart, which I erased, the definition, but we've seen so many times now that TH of U decays a little better than this. This is my gamma naught. This is the gain that we have. So maybe before proving the lemma, so any questions about this? This is really an ingenious application of complex analysis, and you sort of have the, if you have subharmonic functions and they are negative somewhere, this negativity propagates. That's kind of a soft statement. You could prove it, using just harmonic measures, but you need some quantitative version, and that is a quantitative version. And it just means that if there is, if it's negative here, it has to be negative in this whole strip, and that's basically the theorem. That's your gain. One thing that one could ask, one should notice here, is that this does not actually involve, this also works. If my xi is a multiple of E1 to start with, then this also works for xi equals to 0, yes, because t is allowed to be any number. Okay, observe that this proof showed that this proof did not exclude the possibility that we are at 0. That's why I was planning to draw this picture. So let me draw this picture here. Here we are. Here is I minus I xi1, say. Okay. And now I show that basically, everywhere here I will have exponential decay. If I have exponential decay here. So sort of a comment, if 0 plus minus E1 is not in the wavefront set of AU, the proof shows that THU of now, I need a real variable. Guys, I need a real variable. Well, x, okay, let's use x. X is real. Is equal to, so now x is real, Rn, and then I have e to the minus 1 over 2h, x minus y squared, u of y dy. It shows that this actually is small, e to the minus delta over h, because imaginary part is 0. See, I'm just taking this. This basically means I'm taking z equals to x plus I 0, is less than or equal to this, But observe that this is just convolution with the Gaussian. So if I multiply this by some magic number, which is h to the power minus n over 2, maybe, no? H minus n over 2, this converges to, as h goes to 0, to u of x, right? But of course, if this is exponentially small in h, then I can multiply by any power of h, and it will still go to 0. But this goes to 0. From this estimate, I see that this actually goes to 0 as h goes to 0. So what this shows directly that u has to be identically 0 of the neighborhood of this point, which is of course our unique continuation statement, you see. So this is a direct proof that if, well, direct, via this complex analysis thing, if 0 plus minus, sorry, if 0 is in the support of u and support of u which is contained inside of x1 greater or equal to 0, this implies directly 0 plus minus E1 has to be in the wavefront set of U. Because if it were not, then we would get this theorem and we would be able to also have exponential decay at xi equals to 0. But once we have exponential decay at xi equals 0, this gives a resolution of identity. And I see that the function has to be identity 0. So in the 5 minutes, I put the proof of this complex analysis lemma in the notes online, because both Hermander and Sjestran, for reasons inexplicable, they prove the lemma in a rotated version, and then say it's the same when you rotate. It's very strange, just to confuse the author. The reader. The author, I'm sure, had it perfectly clear, but the reader. So that's why I just changed the axis for. But then you sort of see this propagation. The idea simply is, well, not simply, but it's a neat idea, is to construct a suitable harmonic function so that you will have on the boundary of this rectangle where you just get very close, where you have a bad estimate, you want to be as close, and here you want to be relatively far. You construct a function so that these conditions here will imply that W plus that harmonic function is 0 on the boundary, or less than or equal to 0 on the boundary. Maximum principle show less than or equal to 0 inside. And then this harmonic function has the correct positivity properties because we use the fact that we had negativity here. And we do it actually, the proof goes only, you start here and go here and then do it like that. So the proof applies to one part of the boundary being here. So it's a nice exercise in complex analysis. So that's it. That's it. And if you are still willing to listen, so I will show to this afternoon an application of this to some concrete problem from real life, Okay, thank you very much. Well, Kashiwara is a genius. And also, this proof is due to Sjestran. I don't know. Kashiwara never wrote a proof that is known to anybody. So it's attributed to Kashiwara by Sjestran. And I understand that there was some conference in Marathia and Grigis and Shapira were telling. And actually, he even says in his book that they explained to him ideas of Kashiwara in a comprehensible way. But it's my favorite theorem in microlocal analysis. Not true, but because it's the proof is you can give it in an hour with all the details. And even though there are other ways to get those theorems that I, for instance, indicated here, this to me is kind of the most beautiful way. Yes. Here? You see, observe that if I know that this point here is not in the wavefront set, so this I have exponential growth decay, then actually I have exponential decay, of course with constants, which depends how deep I go down, because they depend on this A. But I have exponential decay everywhere. But in particular, I have it at 0. Yeah. And then even though we don't do wavefront set at 0 typically, we do this where functions don't depend on age, because then, but what happens? You show that U has to be 0 simply by resolution. You see, if there is no psi, then this is just convolution with a Gaussian. And then modulo, well, so I should put, since maybe it's all recorded, so I should say there's some constant here which depends on the dimension, but the constant is different from 0. so it's not. That's the whole point. You see, that's the whole point. This has to be 0. So what this means is that if this guy is not in the wavefront set, then the distribution has to identically vanish in the neighborhood of 0. Neighborhood, because x, you see, this holds for x, you see, this holds for x in, so x is Rn, but this estimate holds in some neighborhood of, real neighborhood of x. Huh? Because all our estimates, you know, z prime is fixed, but we can move it a little bit. And this guy here, of course, we move it here a little bit. Mm-hmm. Sure. Oh, please. Well, yes, but you, well, yes, of course, but the question is to have a quantitative result which does not depend on the function. That's the key. See, it only depends on the estimates on the function in this rectangle, and of course, this assumption minus b squared over 2. And the point that this negativity on the real axis propagates along the imaginary axis. And the proof goes by considering just the upper rectangle or the lower rectangle. And then we have various, this is where we have this minus b squared. So you choose your harmonic function in a good way. And it's important that this is very small. You know, where you have a bad estimate, you want to get as close to the good estimate. Where you have a good estimate, you allow yourself to go. And that's also good, important to be able to go all the way. Yes, well, yes, I will finish this one here. I think that was the idea. No, I'll take this one. But this is what Alex brought this from. No. No, I rather eat the part which is analytic, you know. So that's why I mean, the proof goes like that. Okay.